This video is a quick thought on effusion and diffusion, which are processes of gas molecule movement here at the end of the chapter. So this section is going to talk about the difference between effusion and diffusion and define Graham's law. So we talked about the movement of gas molecules and how they move constant, random, and straight line motion. The gas molecules move around randomly in space. And another property of gases we're familiar with is that gases fill their container. They take the shape of their container and the size. They take up the entire container, no matter how much gas is placed in it. And this is a process. When you first insert a gas into a container, there are a few seconds before the gas fills up the entire container. And so effusion and diffusion describe how the gas fills the container. So let's draw a container for ourselves here. And we'll put a barrier in the middle so that we can watch the process of the gas filling the other half of the container. So here are some gas particles randomly distributed in the container only on this side. And they are moving in constant random motion in straight lines. And so on this side of the container, there is a high concentration of that gas. And on this side of the container, there is a low concentration. So let's look at the movement of these particles if we were to remove the barrier down the middle. So there's the same container. If we remove the barrier, the particles from the high concentration side will continue to move randomly because, of course, they don't know that the barrier is gone. But as they start to move towards the barrier and the barrier is not there, they continue to move into the other half of the container. And eventually, the particles fill that entire container with an even distribution. Oh no, how many were there? 3, 4, 5, 6, 7. Now there's 9. Okay, we better add 2. Okay, so now the same number of particles are filling up a larger space. And so this process of the particles moving from high concentration to low concentration to fill up the entire available space, that's called diffusion. And so this movement, this diffusion of particles or energy or objects from high to low concentration, this is a really important feature of chemistry. This is an important driving force for how we explain how all kinds of reactions take place. This is an important driving force. I talk about this a lot in my own research to help explain why electrons move in the way that they do. And if we wanted to draw a distribution like we did for the Maxwell distribution in the last chapter, we could sketch a quick one here. So if we have the number of molecules on the side and we look at the position of the particles, in our first picture, we have a high number of particles, an abrupt change, and then we have 0 particles because there's nothing on this side and everything is on this side. And if we were to draw that distribution again for the after picture, after diffusion has occurred, we would have a lower value for number of molecules that was constant all the way across. So this is the process of diffusion, going from all or nothing to evenly distributed throughout. Okay, and then let's do the other process. So let's say again, we have a container with a barrier in it. and some particles randomly distributed, moving in straight random motion. And this time, instead of removing the entire barrier, let's open a pinhole. And that the pinhole is into a part of the container that's under vacuum. So there's a difference in pressure. There's very low pressure on that vacuum side and high pressure on the other side. So if we open a tiny pinhole into that low pressure side, we'll say it's like this. There's a little gap right there. The particles are going to distribute like they did in the previous one, but they're only going to be able to spread through this tiny little slot. So only when their direction of movement takes them through that slot are they going to be able to distribute. So the movement looks like this, going through into the container. So that process of moving through a pinhole into a very low pressure area, that is called effusion with an E. So it's a slightly different process. And effusion is related to something we talked about in the last video, the root mean square speed, according to Graham's law. Unfortunately, not Graham, our inorganic professor. It is someone whose last name was Graham. So if we want to calculate the rate of something, that is always the number of times that it happens over a unit of time. So the rate of effusion is the amount or the number of gas particles passing or fusing through that hole. Over some unit of time. And as usual, when we want to get a rate for a large number of particles, we want to take a snapshot. So we want to pick one point. So we pick the root mean square of the rate, because a rate is a speed. And so our rate equals the root mean square speed of effusion. And we know that formula already. We've seen it in the previous video. So the root mean square speed is related to the temperature and the molar mass. So it depends on the conditions, and it depends on the identity of the gas. And especially in terms of the identity, we can see that the rate is proportional to 1 over the square root of molar mass, just like we talked about. And I want to give an example because this seems like something that's difficult to relate to. When have you ever had a box with a vacuum on one side? Probably none of you. But one thing that you probably have had is a balloon. And I know I have slightly abused my balloon privileges by drawing it so often in this chapter, purely because I'm not very good at drawing gas cylinders. But a balloon is an okay representation of an effusion situation, because a balloon is not actually a physical barrier that blocks everything from escaping. We know that's not what happens to balloons. Balloons eventually decrease in size and they get small and they don't float anymore over time, because balloons are made of a polymer stretched very, very thin, and that polymer is slightly porous. It has a few very tiny pinholes in it that gas molecules can escape through. And this is why the balloon gets smaller over time. But the rate at which the balloon gets smaller depends on what gas is inside of it. You might have noticed a difference between a helium balloon and a balloon filled with air that you've blown up yourself. So let's say we have two different balloons here. Let's say we have a helium balloon, the super fun kind that we get from the circus back when we could go places. And let's say we put something heavier in the other balloon. We put in air, or in this case, I've put in argon, because argon is a very heavy gas that chemists have access to playing with in the laboratory. So let's say we wait. We let them sit in our living room overnight because we had so much fun with the balloon the next day. What is going to happen to those balloons? The balloons are going to look smaller, but which balloon is going to look the smallest? So let's look back at our formula. So we know that the rate of effusion is inversely proportional to the molar mass. So that means that lighter gases with a lower molar mass, those are going to effuse fastest. So if this number is small, for the molar mass, the rate is going to be largest. So what that means is our lighter gas, helium, that balloon is going to be the smallest and the shriveliest overnight compared to the argon balloon, which has maybe only decreased in size by a little bit. Helium particles are the smallest, so more of them have been able to effuse out in the same amount of time as only a few argon molecules have been able to effuse out. So the rate of effusion, just like the root mean square speed for velocity, happens inversely proportionally to the molar mass. This has been a video on effusion and diffusion. The last video is about non-ideal gases and how all the assumptions we have made in the last 7 videos are not always exactly precisely true.